Hello, and welcome to the session. So my name is Simon Whiteley, and I spend a lot of time working with data lakes and Azure and building giant Parquet big data kind of systems. And it's been a really interesting time in the past year. So data lakes used to be really good at certain kinds of problems. They allowed you to really do some interesting scalable problems, deal with lots of different data types, do lots of different really hard things. But they're quite tricky. You have to work with them in a very specific way. Now, in the past year, that's changed. So this thing called Delta has come along, and it's a new file format based on Parquet that really makes things a lot easier. It makes it a lot easier to do some things you think of as really common in data warehousing that used to be very hard in data lakes. So I'm going to take you through that. So a little bit about lakes, a little bit about Parquet, what this Delta thing is, and what it's unlocked, which is a new way of thinking about data lakes they call the data lakehouse. And we'll have a look and we'll see what it actually means. Okay, so this is me, Simon Whiteley. You can see me. Hello. And I run a company called Advancing Analytics. And we're a consultancy in the UK that deals with all sorts of analytics problems, commonly either data engineering, data science, or that sweet spot where they meet in the middle. And we spend a lot of time working with Microsoft. We're Microsoft partners. And we're always looking at what the next thing in Azure is and how that's changing and how we can improve the architectures and patterns people are using. But also, we're Databricks partners. And so we spend a lot of time talking to Databricks and figuring out what's the next crazy thing they're coming out with. And Delta is by far one of the biggest innovations to come out of Databricks in the past year. And it's really changed a lot of how we work. Okay. I'm also an MVP in the data platform, so that's a thing. Okay, so we've got this thing, the data warehouse, and it's familiar and we work with it a lot, and it's really good having a real managed, structured data model that we can give to the business. We can do reporting on it, we can audit it, we can work very closely with it in a disciplined manner. Now, there's a bit of a backlash against it. It's going, it's too rigid, it's too slow, it's not quick enough to adapt to change. And so a lot of people jumped and went, I'm going to build a data lake. And that just meant they threw a load of files into a distributed storage and went, it's now a lake. And it's been an interesting journey with data lakes as they've kind of gone this massive hype curve, everyone adopting one, everyone building a lake, not many people doing it very well. And then going, well, this is disorganized. And when people started, they just had like Csvs. They just took some straight data, comma separated, threw it into a lake. And when you're dealing with text data in a lake, the CSV doesn't know what structure it is. It doesn't know how many columns it has. We have to figure that out when we read it. So that's kind of has a thing called schema on read. And that means we're always having to kind of figure out what structure should it be. Compression in CSVs, it doesn't really work that well. So there's a lot of problems with using that. And that's where Parquet came along. So Parquet, similar to SQL Server's column store indexes, it's a columnar store. So we're taking data, rows and rows of data like we had in a CSV, we're storing it by columns instead, and that means we can compress it really well into very efficient files. So Parquet is great, and it has a structure. So we try and query some Parquet. We don't need to say, this is the structure, go and work it out. We just say, just read it. It knows what structure it is, the same as a SQL table does. But then an evolution from there. Parquet has a load of things that don't happen automatically. You have to know how to work with it. There's a lot of patterns you have to use to get around it. Again, similar to when SQL Server column store indexes first came out, they were read-only. And so we had all sorts of patterns to kind of update it and then put it somewhere else and then put it back, and it was a whole mess. And we're dealing with the same thing when we're dealing with Parquet. And that's where Delta came in. So Delta is a file format, the same as CSV and Parquet, except it's kind of a wrapper. So the data lives as Parquet inside it, and it gives us a transaction log around the top, which allows for things like transactional consistency, governance, auditing, real deep, heavy performance tuning, loads of stuff that Delta gives us. And we're going to talk about what that does. But one of the big things is that evolution at the top, that from a warehouse to the lake, and then going, oh, I missed some of the nice features of a warehouse. That's kind of where Delta puts us. The next step, we're going, well, I want all the good stuff about a lake, all of that scalability, all of the flexibility, all the agility. But I also want all of the good, strong management features and discipline and auditing and governance and strengths of the warehouse. So actually, when we're saying about this thing at the end, this data lakehouse, we're not saying it's an evolution of those. We're saying it's a combination of those. So it's a all the good stuff of a warehouse, all the good stuff of a lake, wrapped into this data lakehouse package, which is pretty cool. Okay, so what do we actually want from this thing? We want all the good bits from the warehouse. We want it to be structured, governed. I want to be able to check when users have gone and deleted data and roll it back with a backup if I need to. I need to be familiar. Never, never overestimate how useful it is for things to be familiar. If someone comes along and says, I've got a brand new technology, you're all going to love it. You can write in SQL. Everyone goes, okay, sigh of relief. We can use it. We know SQL. We know how SQL works. And that is a real strong feature that often gets overlooked. And it's fast for specific things. Like single record lookups, that kind of stuff, it's great at. Doing certain joins, it's optimized for. It's a relational engine. Doing massive aggregations over huge amounts of strings and that kind of stuff, not so much. You can kind of do it, but you end up having to throw a lot of power at it. Now, on the flip side, in the lake world, they're super flexible. Like, just throw some more data at it. You don't even need to define it, and you can just land it in the lake. You can start capturing the data as soon as you see it. You don't have to do any upfront planning and deployments and code releases. Super, super, super flexible. And it's super cheap. You know, it's normally a quarter or a fifth of the price to keep data in a lake than it is to keep it in a warehouse. Real big cost arguments for using lakes. And massively scalable, it's distributed. And it's fast. But for different things that are warehouses, it's really good at doing that, scaling over lots of data, doing aggregates over huge amounts of data. And so what we need is actually all those good parts of the warehouse, all the good parts of the lake, and bring it together. And that's what the data lakehouse is trying to say. I want all the flexibility of the lake, all the good stuff, all the scalability and the kind of the file patterns that we've got. But I want a layer over the top. It gives me transactions. It gives me governance and an audit layer. It gives me real kind of neat, deep index tuning. I want file management utilities. I want all of the maturity, and that's the keyword, maturity of a warehouse, and all of the agility, big data-iness of a lake. And that's what we're trying to build. That's the aim for most people these days, is this data lakehouse paradigm. So let's talk about files. So we've got this evolution. So CSV, Parquet to Delta Lake. Why did we do that? Have a bit of a look. We can step in and go see a notebook. So this is inside Databricks. This is a notebook I've got set up, and I've just done a few quick example things we can have a look at. So I've got some sample data. So I'm going to say what's currently in that data. You can see about a Databricks data set. It's the NYT taxi stuff. Everyone loves it. And that's coming back and saying that is roughly, how big is it? Oh, it's about 119 meg. Okay, it's not too big. That's fine. We're going to read it in, and we're saying when you read it, infer the headers. So I want to work out what the column names are. Infer the schema. I want to know data types. The CSVs don't have it. And we can tell Spark, work it out on the fly. However, 120 meg file, not crazy. It's zipped. So it's csv.gz, so it's gzipped. And that means this becomes single-threaded. Spark's all about parallelism, all about running lots of queries in parallel. If I have to single-thread things, suddenly things go slow. So just to define the schema, took 30 seconds. Not very good. So to then say, I want to go and write it down to the disk. So I'm taking that data frame, taking that CSV that I've read and defined. I'm saying I want to write it out. I want to include headers when I write it out. Overwrite it if it already exists, because I've run this demo a few times. And then put it there. And again, that took 43 seconds for 120 meg. It's not very good. Because the way Spark works is when I run that, it's going back and it's reading that file, and it's reading that CSV file, the zipped one, that's causing us pain here. Okay, then writing out as Parquet takes about the same amount of time, because I'm still going back to the zipped CSV. The zip is our problem here. But I've now got three options. I've got a zipped CSV, I've got an uncompressed CSV, and I've got Parquet. I'm going to have a quick compare of what they actually look like. So we've got our zipped CSV as expected. That was about 120 meg-ish. We've got our uncompressed CSV. So we can see there's some metadata that gets created. And there we go, that's our big long CSV. And that is going to be, 600 meg. So it's uncompressed it a lot. So that's much, much bigger than it used to be. And then we've got a Parquet file. Parquet file has been created, and it's about 140 meg. So interestingly, it's not compressed it as well as the CSV had. And that, with Parquet, all depends on the type of data, and if it finds efficiencies in there, it'll compress it really well. In this data, I don't have that many efficiencies. It's really interesting what this is going to mean. So we can do this. So we can say spark.read CSV, spark.read CSV, spark.read Parquet. And we can run those different jobs. So that's saying, go back to that flat file, run a job to actually just bring this thing in, and then I've got a dot count at the end. I'm saying, I want you to go count my data. Tell me how many rows I've got. The first one, 14 seconds. So that uncompressed CSV, even though it's smaller than our uncompressed CSV, so we've got our compressed one, that .gz took 14 seconds. Our uncompressed took 5 seconds. That's all about parallelism. So in this one, when we tried to read it, we had to read it in one by one. I can do one task at a time. You should be able to see, we can see in here, 8 at a time. Weirdly, doing 8 things at once finishes quicker than one thing at once. Kind of makes sense. So uncompressed CSVs are faster than compressed CSVs because of parallelism. But then we look at a Parquet, and that took 0.75 seconds. It's just a lot faster. Part of that's because Parquet does have some stats in there and it can cheat and go to the stats. But otherwise, column store is just faster for this kind of thing. So Parquet is a speed demon when it comes to aggregate style queries, and just so much better than having just straight CSVs. So there we go. We like Parquet. If we look at the counts that we get back, actually, I was trying to make it a fair fight. Whereas both the CSVs, they brought the header rows back as data rows. If I tried to strip that out, all the counts would be even slower because it has to do that first. So I was trying to be nice, and still it's slower. Okay, so we liked Parquet. Parquet is very, very good. Okay, let's carry on from there. So the reason why Parquet is good. So we've got our CSV file. I've got loads of data, all mixed up. And then when I change that from a CSV file into a Parquet file, I do this compression. It's compression I can only do because I'm no longer storing it row by row by row. So storing each column as a separate block of data, I can do some interesting things. So that first column, I said, well, the first 3 rows is A. Instead of actually storing that as lots and lots of strings repeated, just say, well, what the string is times how many times it's repeated. That's a thing called run length encoding. And that can only happen when we've got runs of contiguous values. So the more repetition there is in your data, the better Parquet compresses. So Parquet is great for things like dimension values when you've got hierarchies and that kind of stuff. For facts, when you've got a load of measures and a load of things that you can leave on the fact table and it'll just compress it really well. I mean, you can do distinct counts so quickly. So the compression that you get is really, really good. It also does dictionary encoding. So when I've got Fred and Bob, I've just got 1 and 2 now because that's smaller. So it can be compressed more. So lots of things inside a Parquet file that just make it efficient and good. It's a good data storage mechanism. And then along the top, I've got some metadata. So I can see the schema, the structure. Why in my examples for the CSVs, I was saying, go and work out the structure. For my Parquet, I'm saying treat it. It knows what structure it is. I don't have to tell it what structure it is. The same as a SQL table. I can go select star. I don't have to say select star, by the way, here's what the columns are. It just knows because it's got an implicit schema inside it. Okay, so why don't we like Parquet? Why are we changing? What's this new Delta thing going to be? So there's a few problems inherent in Parquet. Now, one is because of that run length encoding, because of that, the big continuous sprees of repeated things is what gives us the good compression. If I'm repeatedly inserting into my table, I'm going to have like tiny little Parquet files. Because a Parquet file is immutable. I can't go and edit a Parquet file once it's written. I can't just append onto the bottom of it. I just need to make a new file. So every time I have a transaction, that's a new file. Anytime I change anything, that's a new file. Meaning Parquet, you'll end up with tons and tons and tons of small data if the data changes a lot. And they don't compress very well at all. Which means big chunky Parquet files, great. Tiny little ones, not so good. But that tends to mean you're picking everything up and repacking it, and you spend a lot of time managing file size in order to have any kind of performance. So it's awkward because these small files really, really impact things. So in this example, I've got 1 big file, I've got 2 small files. And if you think about it, that 1 big file can compress a lot because it's got lots of repetition. The 2 small ones, they don't get as much, so they end up bigger in total than my 1 big file, which is weird, but it's because of that efficiencies of the bigger the file, the more compression you're going to get because of run length encoding. It's a big, big thing. Okay, so other problems. So it has metadata inside the file, but that means that every Parquet file has metadata inside the file. Meaning I'm trying to read something, quite a lot of times I've got to read lots and lots and lots and lots of metadata. I'm opening up loads of files to go and check something. So the metadata is not very scalable. And that starts to be an issue when I'm doing lots of big update queries and checking schemas and doing lots of things. It starts to slow down, which is no good. Complexity, right? So we said familiarity is what it's all about. If I'm saying delete from my table where something equals something, and I can't do that in Parquet. SQL doesn't work. It works for a lot of stuff, but operational SQL, like delete data, doesn't work. So for Parquet, I'd have to say, get my Parquet file, read it into a data frame, filter that data frame, put it back down to this because it's a new Parquet file, doing a load of redundant writes when I'm there, and then probably replace my existing one. And that's fine. That's not a huge amount of work. But you think about making it easy to use, making it familiar for people to adopt this technology, and you say, oh no, you can't update a file. You have to do several different steps to do anything. And people just look at you and go, really? And you seriously use this thing? It's a little stumbling block in terms of people adopting it when they see this type of thing. So, interesting. Auditing. So yeah, I've got my nice delete statement. I'm going, delete from my record, and I forget to put that where statement in. I'm just changing it around, and I comment it out, and I run it. And then all my Parquet's gone. And there's no backups, no rollbacks, no takey backsies. That is done. I've lost all my data. That is horrendous. Now, yeah, I wouldn't write it as a SQL query because we said that didn't work. But if I had that same pattern, so if I had that data frame process and I didn't have a filter in, there's lots of ways I can just accidentally delete my data, which is crazy. And that's a big thing of maturity. Don't have indexes. That's mad, right? So if I say select star from my data where and give it a key, it reads my entire table. It's a full table scan anytime I do anything. And that it's fine because Spark is a nice big chunky cluster, but you're just using a sledgehammer every time, no matter how big the nut. So that's why we need all these things. That's why we're looking at warehouses from the big data line and going, oh, I miss it when it was structured and it had a schema and it was governed. So if someone deleted something, I could roll it back. Two people couldn't try and update something at the same time and get a collision and cause some corrupted data. And just sometimes I just want to write a merge statement. They were the days. And I want to be fast if I'm looking for a single record and not do a full table scan every time. That's like the wish list of why people are complaining about a lake and going, we need to change. We need to do something different. Something has to change. And that's Delta. So Delta is addressing that selection of problems. It's going, here's a load of things that are wrong. We're going to fix them. There's the marketing spiel. So according to Databricks, it's a unified data management system that brings reliability and performance 10 to 100 times faster than Spark on Parquet to cloud data lakes. And that's not a sales pitch for me. Essentially, they are going, it makes things faster. And that's good. There's a lot of people that sales pitch is perfect for. But that's not me. That's not what I'm after. Yes, it goes faster, but it's a Spark cluster and Spark's fairly cheap. So you can just spin up a bigger one. If it's going slow, it's fine. Yes, if it goes faster, I can get a cheaper cluster. Great. But all of those problems that we're talking about, that's not addressed there at all. I mean, data management system is kind of what it's talking about. So what do we call it? So it's an optimized managed format for organizing and working with Parquet files. That makes a bit more sense. So it optimizes them. It's a format. So it is just a file format. We can say I want to write a new Delta file out, and it's managed. So it has some kind of management layer. But it's still Parquet. That's the interesting point. So despite all those things about Parquet files, it's still a really, really good data storage device. So Delta is still using Parquet. We still store the data as Parquet files. We're just adding stuff around it to solve all those other problems. In essence, it's Parquet, but better. I mean, they should hire me to do the Databricks marketing. Delta is Parquet, but better, essentially. It's fine. Okay, so what does it actually do? There's the good sales pitch. Okay, great. We've established Parquet is better than Csvs. It's not hard. We're now saying Delta is better than Parquet. Okay, why? So in this example that we had earlier, so I'm deleting some data. So I've got a data lake folder. I've got a couple of Parquet files in there. And I'm saying, I'm going to delete. Not actually via SQL, but making it simple. So we go delete from this folder where it's equals a segment. And I have to pick all those files up, read everything, filter it in memory. And I replace it. I delete the old ones and I replace it with a new file that no longer has segment number 3, which is big, and it's a big operation, and I'm deleting data. If I delete those files and then it crashes and I don't get my new data, all sorts of problems with that route, which means we end up doing more steps and workarounds, and yeah, pain. So Delta, when it's attacking the same thing, what does it actually do? So when we first create this table, we've still got our 2 Parquet files. That hasn't changed. Again, it's still Parquet. But the moment we create this, we get this Delta log. There's a folder that's just put alongside our data that stores JSON files. And those JSON files are a transaction log. So when I've gone and added in these 2 files, it's gone, okay, you're adding 2 files. And it's recorded the fact that I've added files. It's grabbed some statistics about it. So it knows how many rows in each file. It knows the minimum, maximum value for a load of my columns, the first 32. And yeah, it's just capturing that stuff separately. So if I go, I want to delete some stuff, it adds another JSON file. So I can see I've now got 001 as a JSON file. It still creates a new Parquet file. So that hasn't changed. I still have to go read all that up, filter it out, write it down. Except now I can use that delete statement and it'll work out what I'm trying to do and do it for me. But it won't delete the previous Parquet files, which is weird. What instead it'll do is in the transaction log, it'll tell me it's deleted. It'll mark them as removed. So it'll say, well, I'm adding this new file, number 0002, and 0000 and 0001. They're now removed. They're dead. They are deleted, but only logically. So that means if I come and query this folder, I would see the data duplicate. I'd see all the data several times. If I query the Delta table using that transaction log, then it'll go, you no longer need to look at these files. So I'll come in and I'll say, select off my sales. It'll see that transaction log. It'll see that in the most recent one, it's told me to ignore those 2 old files. And so I'll just read the latest file. So at runtime, when I query it, it's deciding which of all the different files that are still in that directory are the ones I actually need to query to make up my actual file. And that's crazy. It's awesome. Really, really easy. And you can just look inside that JSON and go, what was added, what was removed, what was added, what was removed. And every time anyone makes any change to that table, whether it's a change to the structure, people adding columns, that kind of stuff, whether it's people running a backup archive, when it's people changing the data, doing an insert, an update, a merge, any of that stuff goes in the transaction log, and I can open up and see it and say, who did it? Who deleted all my data? Okay, it was them. Right, roll it back. So I've still got all the old data, and I suddenly have protection. I suddenly have backups. I suddenly have just this layer of maturity across my data. I can do this kind of thing. I can say, well, select with a timestamp. So I can say, well, actually, at this point in time, what did it look like? And that's going to go in. It's going to ignore the latest transaction because that happened after the time I'm asking for, which means it'll say, well, in that case, ignore the new file, which means at that point in time you're asking for, the old files were active. And so I just get a query as of the old one, meaning I've automatically got temporal querying over my data, which is just mind-blowingly cool. So not only has just adding a little transaction log given me kind of a little bit of kind of backup restore, a little bit of protection against mistakes, an audit trail, it's given me temporal querying out of the box just because I can now look at a different active set of files in different queries. So I could run this query and say select star from with that timestamp, compare it to select the current star, and then say what's changed. What happened inside that audit? I can get all the different records that have changed. Suddenly, I can go loads of powerful things. So it's very, very cool. Let's go and have a bit of a look at that. Okay, so we've got our Parquet pane. What's going on with our Parquet? Okay, so we can do this. We can say, well, let's just go and read my Parquet file like I did last time. I'm going to write it into a new one. I'm going to call it my Parquet update. And again, I'm just writing this out as Parquet, particularly special. Leave that to run for a minute. And then I'm just doing a little bit of registry. So if I want to use SQL, if you want to use SQL anywhere in Spark, you need to use Hive. And that's this whole data registry. So I'm creating a database. I'm getting rid of a table just in case I've run this demo before. I'm saying create a new table. From now on, if I go SQLbits.taxis, I just want you to look at the Parquet, so using the Parquet that lives in that location. So it's still in a lake. It's still flat files. It's still the same as it was sitting in my lake. But I'm just saying I want to express this as SQL going forward, which, again, pretty cool. So we'll let that run. And then, yeah, this one. So when that's run, when that's actually come back, trying this and say, well, update our taxis folder, set the passengers equal to 0. But you can see there, no, you can't do an update. You can't do a SQL update. You can't do SQL merge or delete. It's a Parquet file. It doesn't allow that. So I'm blocked from doing that kind of thing because it's Parquet. Again, I can't use my familiar things. So refresh it because I've just recreated that table. And I can do this kind of thing. So this is the PySpark, the Sparky way of doing this kind of stuff. I need to import some functions. I'm going to actually define a table over my Hive table, so I can use a little bit of Hive. I'm saying my new data frame, let's override my existing passenger count with a 0. So that's the same as my previous update statement. I'm now saying set that to 0. That's what I'm doing. Saying there's a new column. It's called the same as things as an existing column, so it's going to replace that existing column with a literal 0. And then go and write it in, and that's fine. And that's quick because we're dealing about small amounts of data. But that's already 3 steps. And it's not familiar. People have to learn that syntax, learn that I have to replace an existing file. It's not just an update statement, and that's annoying. So, okay, let's do it in Delta. So I've got dataframe.write.mode. I'm doing an override. And that's it. The difference between creating this table with Delta and creating the table earlier with Parquet is just that. It's previously I said format Parquet. Now I'm saying format Delta. It's baked in as a first-class citizen within Databricks, which is great. So I can say, go and create it. So I'm going to write it out, saving it in my new location. So I've now got Delta taxis. I'm going to do the same thing. I'm going to register that as a table. I'm going to create a new table using Delta. So no longer using Parquet, now I'm using Delta in that particular location. All right, okay, I can go to that file. I can say, let's see what's happening. It's going to go and create it for me. And then we can try that again. We can say, go and update my passenger count. I think before that, we'll just do a quick, let's just see what the data looks like. So let's go select star from SQL bits and Delta taxi. Just to show you that the passenger, nothing up my sleeves, the passenger count isn't 0. And then we'll do this update and we'll have a look. And we should be able to see, we're just going to do a straight update. It's really, really easy. Okay, so that's going off, running it, show us the results. Passenger count 11222. As you'd expect, taxis usually take people. Then we can run that. Whoops. Running away. And then we can do another one. We can just say, let's repeat that. So select star from SQL bits, Delta taxi. And then we can go and have a look what it looks like. And again, we should see just exactly the same thing, except all my passenger counts are now 0. Now this is going and doing that awkward hops. It's reading all my existing data, it's filtering it out, writing down a new table, it's updating that Delta transaction log to say something's changed. But it's doing it just straight without me having to worry about it. And it's taking a little while. Shouldn't be taking that long. Okay, so it's gone off, it's updated it. So look at that table again. We should then see passenger count should now be 0. There we go. Easy as that. We can now use familiar update statements because we're using Delta, because it's going through this management layer, even though it still is Parquet. And we can see this useful thing. So describe history just says what's happened in this table. So I can see my different versions. I can see it started off, the very first version of this table was a write. You can see I came along and did it. You can see some of the settings I had. I can see the notebook and the cluster ID. I've got an audit log. I can see what's going on in there. I can see the number of files and the number of rows that were written. Just captured automatically. I can see I did an update, and I can see actually the number of updated rows, the number of added files, the number of copied rows. So actually, if I'd said I only wanted to update a single record, you'd see all the other ones would be by copied row because I just had to replicate them. So loads of cool stuff in there just by the fact I've just said, make it Delta. And it's still Parquet under the hood. It just gives us loads of extra stuff on top of it. So that is why we like Delta tables. Okay, so some extra cool stuff that Delta can do. So I've got a nice big table. And then, oh, wait, no. Yeah, that table's got 4 columns. I've only got 3 columns in my table. That's just not going to work. I can just try and say append it into my Parquet. My Parquet is going to go, no. No, I'm a 3-column Parquet. You're trying to insert a 4-column. No, it's going to break. Now, if I'm over in a Delta table and try and do that, that's up to me. So I can tell it, no. If it's different, don't accept it, don't let it in. Or I can say, you know what, just auto merge. If anyone tries and it can fit, if you can figure it out and go, oh, it's only an extra column, we can just append that extra column and treat it as if the other values went, no, it's fine. It'll just take it, just automatically append it and start working with it, just baked in. So schema drift is suddenly no longer a problem. And that used to be a big thing in Lakes. If you received a file and it's like, oh no, there's new columns, I'm going to have to read up the entire thing, merge it together, work out what you're going to do with it, write it down again to replace my metadata. Now it's just just insert it. It's fine. We can handle that. So merge, just baked in, schema drift baked in. The merge statement is the SQL merge statement. Nothing particularly new about it. It's just baked in. So I can do my normal merge into the target table using my source table, give some merge conditions, say what happens when it unmatched, what happens when not matched, do an insert, all that kind of stuff. That syntax is all supported. And I can also do it in Python or in Scala. I can drop my language flexibility. That's one of the things with Delta. It's SQL first. It's first party for the SQL stuff, which again is really, really cool. So let's have a look at doing some of that cool stuff. So we can go over this way into our merge. Okay, so let's again, shall we go and delete this if it exists? And then I'm going to create a table. So just creating an absolute blank table. I'm not giving it any data, saying this is the structure, and this is where to go and put it. Hopefully I've not done this before. Otherwise I might have to go and delete some data, but it should be fine. And this is going to create just basically a shell structure. I'll have no data in my actual Parquet. I'll have no Parquet files, but I'll have a transaction log. So I should be able to actually start tracking what's actually happened as we're going through. It's taking a little while to set up my SQL session, so I'll give that a moment. And then when that's done, we can just run an insert statement. And you might notice one thing. So previously when I was running some SQL, I had a little percentage SQL. I was having to tell it, you're in a Python notebook, everything is Python. But actually this bit of code, treat that as SQL. But I'm not here. So actually here said, this is a SQL notebook. Just treat everything as SQL. Don't worry about it. Just this is everything as SQL. I'd have to tell it if I was writing something that wasn't SQL. Okay, so that worked. It's creating my Delta table now, so that's going off and creating that transaction log. And then we're going to insert some data into it. We just make sure that that actually runs. Go, updating the status. Okay, good. So we've got a Delta table. We can go and have a look at that. It's a Delta Lake address. We can go in, we can see we've got a Delta Lake. See we've got address. And then there's nothing, there's no data. Yeah, there's no part. We've not created anything, I'm just giving it a structure. And then I have this transaction file. I've got a transaction log. Go and have a look at that. And as a result, so I can say, okay, I've got some metadata. I've got no add files, I've got no remove files because there's no data. And it makes sense. And then we can work with it. Okay, so I want to do that insert. So go off, insert some records into it. And then, as we did down there, we'll see what that looks like. So, okay, I've got my 3 records, all inserted, all nice and quick. If we go and look over here, we should see I've got a new transaction. Shockingly enough, that's going to be inserting some rows. So let's see, what does it think? So it has, it's added 4 new columns, 4 new Parquet files, which because I did things in an inefficient way. So we look back, there we go, we've got a load of Parquet. And that's not going to be that efficient. Look at that, the kilobytes. Not very good. But it's done automatically. I didn't have to tell it how to manage things, how to do all that kind of stuff. Okay, so I can do this. I can say, I want to make a new temporary view, so basically a temporary table, and that's going to be just selecting another column. So I'm making a dummy row. That is, go to one of our existing customer IDs. We already had customer ID 11. And I'm going to say this is an update, an updated address. And then what we're going to do is just merge. So I want to merge into SQLbits.addresses. So that's my original table. And I want to take my updates. And that's the view that we had just here as updates. I want to join on the customer ID. If it's matched, do a full update. If it's matched, just make all the new columns the same and ignore the old existing record. If it's not matched, insert as a new record. So super generic merge statement, nothing particularly crazy. Let's just run that. Okay, so run a merge. So we should be able to then, again, as we've done here, do a quick look, see what's happening. And we've got an updated address now. So number 11 has been updated. And we should have our next one. So we want to do updates again, maybe another address. This time it's got an entirely different customer ID. So this is the other side of the merge. This should be a straight insert. And then we see what's going on. In this case, actually, wow, it's sneaky. So we've got country. We didn't have country before. Country is not part of that table. Like, we just have end date. There's no country. So we're saying here's a new record that doesn't exist currently. That's a different structure. It's got extra data. And that's where that little feature comes on, that auto merge, saying, if that happens, just don't worry about it. Just put it in. Just work with it. So I'm going to merge again. So exact same syntax, pushing it through, thinking about it. And then when it's done, we can tell it to run the next bit. Doing the merge, writing the new file. And then we should see that update. And then we can go and have a look at what that's actually done in terms of the Parquet. We can go and see what effect that's had. It's a little while. Late at night, it's getting stuck occasionally. There we go. Okay, so that's gone on, updated it, and there we go, we've now got country. It's just accepted the fact that I've added some new data with a different structure. It's part of a merge statement, and it's given me nulls for the existing ones. And that's fine. So really, really cool features that are just baked in. And then finally we've got this history. So we can say, actually show me the different steps this table's gone through. So there's loads of different changes. So my original create table, when I first wrote data into it, I merged and did that updated table, or when I merged again and I kind of added some new columns. And you can see I've got this version, the version 0, 1, 2, and 3. And actually over here, if I go and select my version as of, so my version as of 1, that's my original table that it originally looked like. And it's fairly straightforward. I still have my new customer address. Version as of 2, I can just go in and say, what does it look like? Oh, it's an updated address. As of 3, and we'll see a country column coming in. It is as easy as that to do temporal querying. Now, it's a little bit finicky about timestamps. I had to give the exact timestamp of the version I'm looking for. It can't do a timestamp around this time and it'll find the nearest one. But to be honest, that's fairly easy to write a little query for. But yeah, really interesting stuff. So let's crack on quickly. Okay, managing Delta tables. So this problem, if I'm doing all those little incremental updates, we saw those tiny little Parquet files, and they're no good. Now, we've got this thing, optimize. And that is the Delta equivalent of running a defrag on an index. That's going to take that, then take all my files and go, oh, well, actually just delete all those files, replace them with some big, chunky, well-compressed files. And when I say delete all those files, I mean mark them as logically deleted in my transaction log, not actually delete them. So it's like, this is a little operation I can just run whenever I want, because it's not actually going to stop people working, because the small files are going to be there. The moment it finishes, the new files are there, and it just makes things more efficient. This is a nice offline maintenance job to keep our lake clean. And we said at the start, that small file problem is a massive problem for Parquet. This just fixes it. Really straightforward, really simple, just compact it, just bung them into the same thing. Now there's this special thing called Zed Ordering that I can do at the same time. And so if you've done lots of things with tabular models, and you know that sorting a tabular model on a certain column just means that compression works better. Again, because of run length encoding. If you sort on a column, you're more likely to get contiguous rows and it always is better. Zed Ordering is kind of like that. But instead, if we've got several different files, what Delta has is a thing called data skipping. So if I look at a file and it says, well, my minimum value is 0, my maximum value is 10, the next one is 10 to 20, the next one is 20 to 30, and I run a query saying, well, my value is 15. It's going to ignore the top and bottom file because it knows it's not in between those minimum and maximum values. So it can automatically do something akin to partition pruning just by looking at those min-max stats. Zed Ordering is saying, I want you, when writing the data down, optimizing the data, to actually organize it in a way to improve the likelihood I'm going to skip files. So you're saying, prioritize the fact that if I filter on this column, or this column, then they're likely to be organized in such a way that I can do skipping. So it's kind of like a multi-column, kind of like a sort into certain columns to improve the chance of me actually doing some data skipping, which is really, really cool. I just run that, optimize my table, Zed order by. Again, it's a SQL first one, so I can run it in SQL. And it's just familiar. So in that example, if I've got various different tables, and I'll say, where's Brad? Go find Brad. And this is all kind of our index finding. How do I find that particular thing? In this case, I'd read all my data. One of them, I don't happen to have Dan and Jan in there, and then I'd just skip it. Jan, Dan, Brad's not in the middle of those two, so actually I can skip one file. Now, if I want to do a good optimizing, then actually Optimize always does that file compaction. So I'm going to take my files, take my 4 different files, I'm going to squeeze it down to 2 different files to make it more efficient. But then you can see how I've organized my people. So all those different people I had in my original files, I've now organized it alphabetically because I Zed ordered by name. So my first file, I've got Andy, Bob, Brad, and Dan. My second one, Fred, Jan, Tim, and Tom. So when I come and run that query again, I can skip that whole file. I can do it a bit more chunkily. Now, if you imagine this is running across huge swathes of data, I've got like big chunky queries I'm running, that's going to get even better and even faster. Finally, I can do this thing. I can do auto-optimize. Now, auto-optimize is kind of similar, except it's doing little 128 meg files. So as soon as I write, the moment I write, it goes, ooh, I'm about to write down as 4 tiny files. Why don't I just make that one big file? And it'll kind of interrupt the query plan just to say, you know what, let's optimize that right. Let's try and get 128 meg files. The other one, auto-compaction, is after I've finished writing, it looks back and goes, right, what files are in that folder? Should I do a little bit of tidying up? Again, looking at 128 meg. Now, that's different to optimize. If I run optimize, it goes for 1 gig. And 1 gig, about 1 gig for Parquet file is kind of like the optimal. That's what we're looking for. 128 meg is a bit small, but it's quite nice. It's a neat minimum file size to be doing every time we write. So optimize writes, auto-compaction, you can turn it on. You can turn it on a given table. You can turn it on your entire Databricks cluster, and it'll just work that out, doing 128 meg files. And then you can run an optimized job later that will go clean everything up into those nice big chunky 1 gig files. So we've got nice performance, we've got compaction, we've got the equivalent of index defragging that's happening inside our table. And if you think how far we've come from the start of going, I've got a CSV, I don't even know what data's in there, to I've got a whole management layer of working with things and an audit log and time travel. That is huge. So in this case, I've got my Delta table. I've got some chunky files, lots of small files. I've been working with it a lot. And then I come and say, right, there's 8 chunks of data I want to try and write into it. So to illustrate those 3 different things, optimized writes. I'm no longer writing 8. I'm taking those 8 and going, actually, that's more efficient as 2 files. And so it's interrupting, changing my plan, optimizing it as I go. Auto-compaction is going to go, well, all those tiny files, like we can clean that up. While we're there, let's fix that. So packed everything into 2 chunky files. And then after the fact, if I run an optimize, that's going to clean up all those files into big chunky 1 gig files. So they're my different options for making things run really, really fast and kind of just better optimized. So let's have a super quick look at that. So again, we've got this describe detail. So we can have a look at that, and that'll tell us essentially how many files is in a given folder. So we can go off and run that. That'll tell us, ooh, how many have we got? I've got 5 files. That's not many. I've got a tiny amount of data, and it's across 5 files, which is rubbish. Then I've got this one command, my optimize command. Oops. Oh, I sent it to the wrong place. So my optimize command, I can just run on this one tag. Here we go. It'll go off, run it. It'll tell me what it's done when it's finished. It says, okay, right, I have removed 5 files, added 1 file, taken 5 small files, smashed all the data together into 1 bigger file that's a lot more optimal. And then if I run that finally again, then we should see I've now got a single file and it's working quite nicely. There we go, 1 file. E at P times. Okay. So all of that together, all of that additional functionality, that our wish list we had at the start. So I want it to be structured and governed, familiar and fast. They're things Data Lake never had. Well, now it is structured. So I've got a schema, I've got schema management, I can manage schema drift. Governed in that I can see a transaction log, I can see whenever someone went near it, I get a log. If 2 people are trying to write to it at the same time, the transaction log actually manages that. So I'm protected. If someone accidentally breaks the thing, I can roll it back. I've got the full history. I can control how long I keep that history for. That's a level of government you never had for any kind of data lake. It's familiar. As you've seen, we've used SQL. We can just write SQL to manage so much of it, and that's crazy that it is just so efficient that we can work with it that way. It's fast, because it's got the index seek kind of things from that Zed Ordering stuff, plus it's got the scalability of Parquet and how that manages. It's bringing both those together. I've still got all the flexibility, the cheapness, the scalability of my lake. Now, on the other side, when we've got those small files, operational complexity, actually, well, small files are gone, because that's fixed by optimize. I can go and clean that up as we go. Operational complexity, well, now I've got delete and merge, and I can simplify code into the things that I'm familiar with. It's very auditable. And I've got indexing, I've got management, I've got go and like look after the table in an offline maintenance job if I want to. So actually, my problems are all gone. So what I'm left with is this brilliant thing that sits in the middle. It is this combined abilities of a warehouse and the functions and features of a lake in this one system. So it's when you kind of get this was the idea, this modern warehouse, and that's the kind of thing certainly I've been building for a long time, is this get some data into a staging area in a lake, pick it up, shape it, clean it, put it down as a Parquet file, and then put it into a warehouse and then serve it out to users. We've got different people there. I've got my data scientist using Databricks directly to go and do some data managing. I've got my reporting engineer, my BI person, building something in the actual warehouse, doing SQL heavy stuff. My report users are over there using Power BI. Now, what we're saying is actually, or certainly at least what Databricks are pushing and kind of what there's a huge strong movement towards, is this of saying, well, actually, that whole curated star schema type thing, just have that in your lake, because we've now got the tools and we've now got the maturity to deal with those kind of data models. To actually have several layers of your lake. And then actually, your data scientists and your engineers are all using the same tool, using the same bit of compute. They're using the same set of languages. They can share notebooks and environments and features and functions and go over the same data. Your Power BI users, they're coming off and accessing through that saved there. So when I was saving things as that SQL bits taxis, I can then expose that as a table that Power BI could see, and they can go bring that table in. They don't know that under the hood, it's this transaction log wrapped Parquet file. But I can just expose that by going through Databricks as a querying layer, and suddenly I have an incredibly powerful system at my hands. That is what the data lakehouse is all about. So hopefully that message is clear, that data lakes have moved on a long, long way since their start, since the ideas of saying it's just a free-for-all that you can use to build some crazy system that can scale crazily. Now it's a mature, managed, very sophisticated data management platform that can do a whole load of stuff that we can do with warehousing, plus a whole lot more, because we've got the flexibility of lakes. And that is pretty darn cool. Okay, so I've been Simon Wiley. Thank you for listening. I'm hanging around in the comments answering questions and generally being a nuisance, so feel free to pester me with questions about Delta and Spark and next generation data lakes and all that kind of stuff. I'm on Twitter, so feel free to ping me. And I do lots of these videos on YouTube. So if you're interested in Synapse or Databricks or Delta, then catch us on YouTube and I'll sure to be talking about more and more stuff. All right. Hope you enjoy the rest of the conference.